Hey everyone, welcome back with a new lecture from Accredited Laboratory. As we discussed before that you can use F-test and t-test to compare between two groups of samples or two populations. You can compare between two instruments using to analyze the same target analytes or two methods using to analyze the same target analytes, but how can we compare between more than two groups of samples? ANOVA, or analysis of variance, is a statistical test used to check if the means of two or more groups of samples or more than two populations are significantly different from each other. So ANOVA used to compare between the means of more than two groups of samples. If you have three instruments or more, or three methods used to analyze the same target analytes, you can use ANOVA to compare between the performance of all of them. Also, ANOVA used to check the impact of one or more factors by comparing the means of different samples. As example, in medical field, if you want to compare the effect of different type of medicines on a specific disease, you have different type of medicines, 2 or 3 medicines used to cure the same disease. But you want to compare the effect of all of them on this disease, but for sick persons with different ages. You will use ANOVA to do this. As example for that, if you have 2 or 3 medicines used to cure blood pressure, and you want to compare the effect of these 3 medicines on the blood pressure, but for sick persons with different ages, from 10 to 20, from 20 to 40, from 40 to 60. So you have 2 independent variables, and you want to test the effect of 2 independent variables on one dependent variable, which is the disease itself, the blood pressure. You have first different type of medicines that will affect on the disease but will not be affected. So this is independent factor. And another independent factor, which is the ages of sick persons. So the disease will be the dependent variable, and the type of medicines and ages of persons will be the independent variables. Also used in the medical field to prove if the medication treatments were equally effective or not. As I said, if you have different type of medicines used to cure the same disease, and you want to prove if all of them are equally effective on this disease or not, you can use ANOVA to do this. ANOVA divided into 2 types. One-way ANOVA and two-way ANOVA. One-way ANOVA, only one factor will be studied to know if there is a significant difference between the means of more than 2 populations or not. As example for that, if you have 3 instruments used to analyze the same target analytes. In this case, you want to compare the performance of these 3 instruments to analyze the same target analytes. So you have only one factor will be studied, which is the accuracy of these instruments to analyze the same target analytes. So you can use one-way ANOVA to do this. So if you want to compare the effect of performance of 3 instruments used to analyze the same target analytes, you will use one-way ANOVA. And in one-way ANOVA, you have one independent variable and one dependent variable. Independent variable that will affect but will not be affected. The instruments or accuracy of instruments will affect on the target analytes, but it will not be affected by anything, by the target analytes. And also, the target analytes will be affected by the accuracy of instruments. It may be different from an instrument to another. It may increase or decrease from an instrument to another. So this is the dependent variable. So independent variable that will affect but will not be affected. Dependent variable that will be affected but will not affect. But in two-way ANOVA, you want to test or study the effect of 2 different factors at the same time. And here, 2 factors will be studied, not only one factor like in one-way ANOVA. So you will have 2 independent variables, which are the 2 factors, and one dependent variable. And that's like the example I mentioned before. If you have 2 or 3 medicines used to cure the same disease, and you want to compare the effect of these medicines on this disease but for sick persons with different ages. In this case, you have 2 independent variables, which are medicines, the type of medicines, and the ages of sick persons that will affect on the disease but will not be affected. So these are the independent variables. And you have dependent variable, only one dependent variable, which is the disease itself, because it will be affected but will not affect on anything. So you can use 2 ways ANOVA to study the effect of these 2 independent variables or these 2 factors on the dependent variable or this disease. And another very important point you should know about ANOVA, that ANOVA uses a null hypothesis and an alternate hypothesis. In null hypothesis, when all the sample means are equally same or they don't have any significant difference. If you want to compare between the means of more than 2 groups of samples or more than 2 populations, and you found that the means of these populations are same, in this case you don't need to do any other test. You proved that they have the same effect and they have the same performance. But in an alternate hypothesis, when at least one of the sample means is different from the rest of other sample means, if you will compare between the means of 3 populations and you found that one of them is different from others, but still you are not sure which one of them is different, so you have to do another study or another test, and that will be explained after that. You will do, there is a least significant difference, and like Ponferroni approach and other approaches also used to prove or to check which one of these means is different from the others. And now let's have example for one-way ANOVA, then we can do this also using Excel sheet. As we have in this example, you have 3 instruments used to analyze the same target analysis and you want to compare the performance of them. So you will prepare 6 to 10 replicate of samples spiked by the same concentrations and analyzed by these instruments. Better to have the same conditions for all instruments, better to be analyzed by the same analyst on the same day, to be able to compare the performance, only the performance of these instruments to analyze these target analyses. So first you will analyze these samples and you will get the readings, the results, and you will calculate the average for each group, and then you will calculate the grand total G, which is the summation of all readings that you have, and then grand mean, the mean of sample means or the mean for all readings, which is equal to G or grand total divided by n, number of these readings. Then you will calculate the sum square, the sum of squares for all readings, and that you will see in the Excel sheet. That was the first table, and in the second table you will have A, or each reading in group A minus mean of group A that we calculated already in the table 1, and B, or each reading in group B minus mean, the average calculated in the table 1 for group B, and also same for group C. So you will calculate each reading minus average for each group square. Then you will calculate the summation for each one of them, and you will understand exactly how to calculate when we will prepare our Excel sheet. The third table and the most important table is the source of variation. And the source of variation for any test or study are only between groups variability and within group variability. Between groups variability, which is the variation between the distributions or readings of groups or levels, as the values between all groups or levels are different, because if you have different instrument, as example, used to analyze the same target analysis, and you run replicate of spiked samples to compare between the performance of all of them, you will get different results for all groups. If you this will be one instrument, this another instrument, this another instrument, and there will be differences in readings or results between all of these results, and that is the between groups variability. But within group variability here, the errors will be within each group. Variation here caused by differences within individual group, as the values within each group will be different. As here in this example, same if you have different instrument using to analyze the same target analytes and you got the results, you found that the result here in the group are different. Within the same group, the results are different due to experimental error. So results within each group will be different due to experimental error, and this is within group variability. Within each group, group 1, the results in group 1 are different due to experimental error. That's within group variability. To calculate the source of variation between group variability, first you will calculate the sum of squares between groups, which is equal to n1 number of readings for group 1 multiplied to the average or individual mean for each group, the average of group 1 minus the grand mean. Average and grand mean, average for each group and the grand mean calculated in the first table. Square plus n2 number of readings in group 2 multiplied to the average for group 2 minus grand mean square, and so on. So it will be calculated n number of readings multiplied to the individual mean for each group minus the grand mean that calculated in the first table. Then you can calculate degree of freedom. Degree of freedom equal to n number of groups minus 1 number of groups. If you want to compare between 3 groups, or you want to compare as example between 3 instruments, so 3 minus 1. Then calculate MS or mean of squares, which is equal to SS between groups divided by the degree of freedom. Then calculate the source of variation within group variability. First you will calculate sum of squares within groups, which is equal to summation for each reading in the group minus average calculated for the group, and that calculated in the first table, square. As here we have group 1, group 2, whatever groups we analyzed, then you got these results. For each reading, 5 minus 4.9, the average. Each reading minus the average. Each reading in the group minus the average. So plus summation. The reading number 2 minus the average for group 1 square, and so on for each group, and that will be calculated easily using the Excel sheet. Then you will calculate the degree of freedom within group, which is equal to number of readings for the group 1 minus 1 plus number of readings for group 2 minus 1 plus number of readings for group 3 minus 1, whatever groups you analyzed. So as example, if you run 10 replicates group 1, 10 replicates group 2, 10 replicates group 3, it will be 30 minus 3, it will be 27. Then you will calculate the mean of squares within group, which is equal to SS, sum of squares within groups divided by degree of freedom within groups. And to know if there is a significant difference between the means of all groups, you will calculate F statistical and F critical. F statistical, the ratio of between group variability and within group variability, which is equal to mean of squares between groups that calculated in the third table from the source of variation divided by mean of squares within group variability. And then you calculate F critical from using the Excel sheet, and if you found that F statistical higher than F critical, so you will reject the null hypothesis. Null hypothesis saying that all means, the means of all groups are equal, so you will reject this hypothesis. You will use alternate hypothesis, and that means there is a significant difference between the means of all groups. At least one of these groups is different, but still you don't know which one is different. So you will run post hoc test to know which one is different, such as least significant difference. There are other approaches also, but least significant difference is easy rule to know which mean is different. Also, you can calculate p-value using the Excel sheet, and if p-value less than 0.05 or 5% significance level, so there is a significant difference between the means of groups. And in this case, you will run post hoc test to know which mean exactly is different, like least significant difference using this equation. We will do this using the Excel sheet, inshallah. Then if the difference between any two groups higher than LSCD value that you got, so you found which mean is different. And now let's do this using the Excel sheet practically.
I want to compare the performance of these instruments and to check if all of them can be used to analyze these target analytes and get accurate results or not. So I ran 10 replicates of samples spiked with 100 ppb concentrations, and I got these results. Then if I want to calculate this directly from using the Excel sheet, I can go for data, then data analysis, then ANOVA single factor using one-way ANOVA. If you didn't find data analysis here, you can go for file, options, and here add-ins, Excel add-ins, then go. If I remove this selection, okay, data analysis will be removed from here. So I have to go again, file, options, add-ins, Excel add-ins, go and select here, and data analysis came back. So data analysis, then ANOVA single factor, which is one-way ANOVA. Okay, here the input range, all of these results, enter, and labels in first row. Yeah, I added the labels. So I will select this alpha significance level or 5% error, and here output range, you can select as example here, then enter, and okay, these are the results. As I said in the lecture, the most important results here, if statistical, this one, if statistical, p-value, and if critical. If the if statistical or if value higher than if critical, so there is a significant difference between the means of these three instruments and the performance will be different. But if statistical less than if critical, so there is no significant difference. And also p-value, if p-value less than the 5% error or alpha level 0.05, so there will be a significant difference. But here 0.8, it's higher than 0.05, so there is no significant difference between the means of these three instruments. And that means if you have two instruments in your lab and you bought another instrument and you want to check the performance of this instrument, you will analyze as we did that replicate of samples spiked with known concentration. Then if you found that there is no significant difference, so there is no difference between the performance of these instruments, and all of these instruments can be used to analyze these target analytes and get accurate and reliable results. So there is no significant difference in this case, and so the performance of these instruments are equal. If you want to calculate manually using the same example, three instruments using to analyze the same target analytes, and you ran replicate of sample spiked with 100 ppb concentration, then you got these results. First, you will do the first table, you will add the results for each instrument, then number of replicates 10 for each, summation for each group, average for each group, Then grand total, as I mentioned in the lecture, grand total equal to summation of all of these results, summation, but for all results, for 30 replicates. Enter. Grand mean equal to grand total divided by number of replicates. Number of replicates 30. Correction factor equal to grand total square divided by summation of all replicates. So grand total square divided by 30. Then sum square. Sum square, this is function here, sum square. Sum square for all of these data, all readings. This is the first table. In the second table, A minus mean square means each reading in group A minus the average of group A. And B minus mean square, also each reading in group B minus the average of group B square, and also for C. So I will calculate like this, equal to A, this reading, minus average and square. If I calculate it like this, I cannot calculate other reading easily. So I should do in this equation, I should add $sign here, $sign, enter. Then if I move it like this, it will be calculated for all readings. Same here, equal to B minus this average equal to C, just B minus then you calculate the summation for each group. Or you can move like this. This is the second table. The last table and the most important table, which is the source of variation. First, you will calculate sum of squares within group and between group variability. Sum of squares within group, as I said, the difference between results within the same group. So it can be calculated from the difference between each reading and the average. You can get the error or the variation. So sum of squares within group variability equal to summation of all of these results for group 1 plus group 2 plus group 3. Then total equal to sum squares minus this correction factor calculated from the first table. Enter. Then you can calculate between group variability sum of squares for between group, which is equal to total minus sum of squares within group. Enter. Degree of freedom equal to between group, as I said in the lecture, for all groups 3 minus 1, 3 groups minus 1, n minus 1 here, 3 minus 1, so it will be 2. Within groups equal to 30, all results, all readings minus 3 n1 minus 1 plus n2 minus 1 plus n3 minus 1, so it will be 27, and total equal to this plus mean of squares, as I said in the lecture, equal to summation of squares divided by degree of freedom for each one. If statistical or if value, if critical, and p value, which are the most important results, and depending on these results we can decide if there is a significant difference or not. If value at the beginning equal to, as I said in the lecture, the ratio of between group and within group variability equal to between group sum of squares divided by within group sum of squares, enter. If critical equal to, if there is a function here, if n, enter, probability of errors, which is 0.05 significance level, comma, degree of freedom 1, which is between group variability, comma, and degree of freedom 2, this one, enter. P value equal to, if from function also, if distribution x, which is if value, if statistical, then comma, degree of freedom 1, comma, degree of freedom 2, enter. And as I said, if value higher than f critical, so there is a significant difference. But and also if p value less than 0.05 probability of errors, so there is a significance level. Here, if statistical lower than if critical and p value less than 0.05 probability of errors, so there is no significant difference. There is no significant difference between the means of these three instruments, and all of these instruments can be used to analyze these target analytes, and we can get accurate and reliable results using all of them. But what you will do if you found that if value, if statistical higher than if critical and p value less than 0.05 probability of errors? In this example, you will calculate from data analysis, then ANOVA one way, okay, input range, this range, labels, alpha error, output range, here, enter, okay. Then you found that if statistical 11 point and if critical 3.35, so if statistical higher than if critical and p value less than 0.05, so you will run another post hoc test, which is, as example, least significant difference. To calculate, as I mentioned the equation in the lecture, you should calculate t value at the beginning. T value equal to t and this function, probability of error, which is 0.05, and degree of freedom but within group variability due to the experimental error, so all of them, enter. Least significant difference equal to t value multiplied by square root of 2 brackets 2 multiplied by mean of squares, but also within group variability, mean of squares within group variability. Then divided by n number of replicates for one group, because we calculated using within group variability due to experimental error, so you will use 10 number of replicates, 10, not 30. Then enter. came out 10.27. If the difference between any two groups, in the average, if the difference between any two groups was less than least significant difference value, so there is no significant difference. But if the difference between any two groups was higher than least significant difference, so there is a significant difference, and you will know which group exactly. So here, as example, 122 minus, in this average, equal to group A minus group B. Enter. Group A minus group C, or okay, minus group C. Enter. It's 22.9. Group A from group C, and also group B minus group C, group B minus group C, 16.3. so this group, which is group C, there is a significant difference between these three groups or three instruments, and the mean of this group, this is the problem. The performance of this instrument not accurate and should not be used. This group C, the problem was here. The difference, the mean of this group is different than other groups. So here you can say, if you compare between the performance of three instruments, that this instrument cannot be used to analyze these target analytes to get accurate and reliable results, but you can use only these two instruments. That was the end of our lecture for today. I wish that was valuable for you, and inshallah in the next lecture I will explain two-way ANOVA with and without replication. Thank you, and see you in the next lecture inshallah.